To ground this lesson, I wanted to start with the idea of fields and formalizing the idea of fields. Fields we think of as a set of vectors that exist everywhere in a space around an object producing a field. Represents a quantity that associates an influence of an object in a region surrounding that object, and there's no apparent physical connection there. There's nothing connecting those two objects. It's a way of conceptualizing and mapping that field, something that's not visual for us. But we can definitely see the effects of this field on the objects in that region. What we see is that the magnitude of this field changes depending on the distance from the object, but we can study situations or regions where the field is constant in value. Examples of this is gravitational fields, electric fields, magnetic fields, quantum fields. We're going to get into modern physics with quantum field theory, and those are all examples of fields. What we see with field lines, when we draw these lines, remember we're representing a field as vectors, so we're going to think about the vectors and the lines through space created by that field. It's represented by a grid of vectors. What we see is field lines do not cross and field lines are continuous. You won't see field lines from a single object crossing one another. The density of the field lines is proportional to the magnitude of the field. And the example I'm going to bring up for you is a gravitational field. It's proportional to gm over r squared. And I know you've covered the gravitational force, which is gm1 m2 over r squared. That's the force. But the field is represented by just the term with one mass in it. And when I think about the Earth, here's maybe the surface of the Earth, and there is a radius there. There's a gravitational field all around the region of the Earth, and it will point inward towards the center of the Earth. It points radially inward. So when I think about the magnitude of this field, I have a constant value near the surface of the Earth. I can represent this with a vector pointing inward. That would be the field along the surface of the Earth. There may be a taller point on the Earth, and what happens is, because it's a 1 over r squared, that field will become smaller in value. And so when I think about the field, this radius, the top of the mountain radius around, its vectors are going to be smaller than the ones closer to the Earth. So you may already be getting this intuition about how field lines work and how we're going to think about electric field lines from a gravitational field. The field will point inward radially, and I can represent it like this, just inward radially from all directions. And what I'm also going to note here is that the density of the field lines is proportional to the magnitude of the field. So as we get closer towards the center, as r becomes smaller, this whole term becomes larger. And we can see that the density of the field, if I just pick a circle of one radius, I can get all of these field lines in it. Whereas if I go up here and do the same circle, I don't have as many field lines through it. So the gravitational field is not as large in magnitude here as it is here. So at A, it'll be larger than it is at B, and the density of those field lines increases at A compared to B. So that's a foundation in field lines and how to think about field lines. I'm going to move to the electric field. To determine the direction of electric field lines, which is different than gravitational. With gravitational, we only have masses and they're always attractive. But you know, with positive and negative charges, some are attractive and some are repulsive. So what we do is we take a positive test charge and we put it in the field and see what happens. So my positive test charge, and I'll just draw in the drawing here, I'll just put a positive sign here, and this will represent a positive test charge. When I put a positive test charge near another positive charge, it will be repelled away, and that will be the direction of the electric field. So what we see is that the electric field points away from positive charges. And again, if I put a positive test charge near a negative charge, I have a negative one here, it will be drawn towards the negative charge, and that's how we get the electric field lines pointing towards negative charges. And that's how that works, is now we have a direction for electric field lines. General properties of electric field lines, I've gathered them all up on one slide, and I'm going to review different situations where you can see this all being true. And to get it off the top of my list here is to talk about the units of electric field. It's newtons per coulomb or volts per meter. Both of those are true. When you're first introduced to the units of electric field, you're typically introduced as newtons per coulomb, because that's sort of where the definition is. How many newtons does it take to move a charge coulombs in a field? We will learn later in the unit that it's also volts per meter, and that's getting into electric potential. And so I'll leave that for a later time. But both of these are true. If you see them in different places and you're kind of confused, I'll give you that much, because there are two valid units for electric field. The electric field is represented by vectors and adds as vectors. I have some problems dealing with that later in the lesson. The field at a point is tangent to the field line. So I picked a little bit more complicated electric field situation here with a positive and negative charge. And when I look at this, here's the positive charge, the electric field is pointing away from it. What happens is the positive electric field lines will meet up with the negative electric field lines. They will add as vectors, right? And continue to the negative charge. So they'll start, and they'll often say that a positive charge is a source and a negative charge is a sink. And you will see the electric field line sink into the negative charge. So you can see those field lines connect, but because there's more lines pointing away from the positive charge then connects to the negative, I'm going to say that the positive charge is greater than the negative charge. And also when I look along here, I can see the density of the field lines. Like there's, when I draw a circle here, there's not as many field lines as when I draw a circle here. So the magnitude of the electric field here is going to be smaller than the magnitude of the electric field here. The electric field from the positive and the electric field from the negative are adding at all points on this picture here. Everywhere they're adding. We can see at some points they add to some smooth curve, and sometimes they kind of turn. So like if I wanted the electric field at this point, it would be tangent to that curve, so I would put it in that direction. It's eventually going to point towards to the negative, but I draw it tangent there. At any other point, I would also have a tangent line, and you can see it's easier in some of these places where the lines are more straight. But then when they curve, remember you want a line tangent there. Field lines do not cross and are continuous. You see that on the picture here. At every point here, there's an electric field vector from the positive and negative being added, but I don't have different field lines crossing at different places. I'm not going like this and like this. I just draw at that point the addition of those two vectors, and I get a field line. So what we're seeing is that these field lines are continuous. They will flow and they will not be jerky. They're not going to have any sharp turns in them. They're going to be very smooth. They leave and enter conducting surfaces at a perpendicular angle. You can see that here on this charge. Everywhere along here, there's a perpendicular angle between the charge and the electric field line. We will see more examples of this as we move forward with a conductor. And remember, with conducting surfaces, with conductors, the charge is free to move with no inhibition, and we'll have net charge on the surface of a conductor rather than inside. And so what we see is that inside conductors, the electric field is zero. If I had a conducting sphere of some kind, a shell, and I had maybe positive charges on the outside, the electric field inside this shell is going to be zero. All of the charge will reside on the outside, and there's no electric field in there. I've chosen some examples of electric field lines to get you used to thinking about them and looking at the qualities that distinguish the different situations when we have single charges or multiple charges, etc. So here's a simple situation, a positive charge and a negative charge and another negative charge. I would ask you which charge here has the largest magnitude. Well, when we look at it, the charge with the largest magnitude is going to have the largest electric field, which would be represented by density of lines. We can see that there are more lines on this one. So this charge is going to be the largest charge here. It's going to be greater than QB. And I would say QB and QA are equal to one another because they have the same amount of lines coming in and out of them. So this is just electric field lines for single charges. We're going to look at electric field lines for multiple charges. And here we see two negatives. This would also be the same situation as for two positives, except the field lines would point in the opposite direction. So you can see that there's no field lines connecting these two. Field lines will always point towards negative charges, so a field line can't start at a negative charge and end at a negative charge because it would never start at a negative charge. It always ends at negative charges. We can see that there's a positive and negative here, and the field lines connect smoothly between them, and I would say that these two charges are equal in magnitude but opposite in sign because they have the same number of lines on each of them. Another situation we're going to look at is the capacitor, where we have two conducting surfaces that have opposite charge and equal distance apart. And what happens in here is an electric field is created in this region between those two plates. And this electric field value will change as we move from one plate to the other. Typically, in order to look at this electric field, we'll omit the outside here where we have this sort of losing the effect of the constant direction inside the capacitor, these two plates. But it is true that the electric field lines, point out from a positive charge and towards a negative. And if these two are equal, I won't have any extra ones pointing out. So it has to point from the positive to the negative. But now there's this space out here. In the middle here, the electric field line that points this way for this charge gets canceled out by the electric field line that points this way from this charge. So overall, we're left with an electric field that points straight downward. But without the cancellation from other charges along here, we get this rounding, this bending out on the end, and it won't be a constant. It won't follow the same equation as in between the plates. So that's an interesting situation that we'll look at a little bit more in depth in another lesson. Another situation I picked out is a conducting sphere placed in a constant electric field. Notice that there's some sort of electric field here. I might call this the external electric field. I don't know where it arises. It may be because there's two capacitor plates like on the previous example. There's a bunch of plus charges here, a bunch of negative charges over here, and it just creates a constant electric field in between. If I place a conducting sphere in there, I can see that the conducting sphere, this polarization that happens in the electric field, the negative charges will be pulled towards these positives over here, and these positive charges will be pulled towards the negative over here, and these charges will create this polarization on a conducting object. And I know this is conducting because there is a congregation of negative charges over here, which leaves positives over here. So this is a conducting sphere. And what I'm seeing is that the electric field lines must come in perpendicular to the surface. You can see that happening here. And it ends at the negative charges and it emerges from the positive charges. With electric fields for uneven surfaces, the charges will distribute unevenly around that surface. And that's different for like a sphere. You'll see the charges distribute completely evenly around the whole surface because there's no distinguishable features, there's no points or anything. When you have something pointed, the charges will distribute differently, and that has to do with the forces parallel to the surface. When there's a bunch of charges and they're repelling one another, they feel forces along this parallel to that surface until they come to a stop. And so when they're repelling each other and that force is more perpendicular, right? If I divide this into a perpendicular component, this force is more perpendicular to the surface than it is parallel, and that charge won't feel as much of a force to move. So when you have two forces that are next to each other, they're repelling each other more than they're pushing each other down the surface. And so the electric field will be denser near the points here because there's more charges here, and less dense where there's less charges. If I put this conductor into an external electric field like I did on the previous slide, so here there's E external equals 0, and here now I've put an external electric field in here. You can see that the charges are going to distribute. The charges are going to polarize like we expect charges to polarize on a conductor in an electric field, but they're going to be closer on the pointy edge than there are over on the other side. So that's how that works for surfaces that aren't even. And an application of this is the application, is a lightning antenna. We put something pointy on the top of a building, and that attracts the lightning to that object. And it has to be a conductor. And what we see is that a bunch of positive charges will be up on top here collecting together. And here's the electric field. Well, a lightning bolt wants to come in, and it's negative charges, and that's why the lightning bolt gets attracted to the antenna. If you have something rounder, it will not attract a lightning bolt as much as something pointy. So this is the idea. You may get questions in your homework about where's the best place to stand when dealing with lightning, and you do not want to be around something that is tall and pointy and conducting. That will be the most ideal thing to attract lightning. The car, they will say, is the best place to be, and that is because there's some insulation. There's insulating material down here, and so that protects you from the lightning